Support vector machines. In this session we are going to see the basic theory of support vector machines. What is the origin of support vector machines? What is a decision boundary? What is a decision boundary with largest margin? Support vector machine algorithm. What is a kernel trick in support vector machine, and how do we build support vector models? And then finally, what are some of the applications of support vector machines in real world? SVM is one more black box method, we can say. The real theory is not very obvious or not very straightforward to understand, but with some effort we can get clarity on the overall theory behind SVM machine learning algorithm. Compared to other algorithms, SVM is from a totally different approach. It's based on vector algebra, and we in this session will try to learn basic principles, overall philosophy, and the implementation of SVM on a particular tool. But we won't be able to discuss the exact overall theoretical details of SVM in depth. SVM was first introduced by Vapnik, and initially it has been compared majorly to neural networks, and neural network has some issues with overfitting and computation time, etc. SVM algorithm is slightly better at generalization, and it avoids overfitting most of the times, and there are many applications where SVM is much better than neural networks, and most of the times SVM takes lesser runtime compared to neural networks. So to understand the SVM algorithm, we'll start with the decision boundary or the classifier. So what exactly is a classifier? A line that separates two classes, type 1 or type 2. So we already discussed the classification algorithms, or classification is all about finding that particular decision boundary that can separate the two classes. A good classifier or a very good decision boundary is that one that generalizes very well, that should work well on training data as well as testing data. And this classification boundary or the decision boundary or the classifier need not be a straight line always. We might have many classifiers. Classifier need not be unique. There can be many classifier that does a good job of separating good from bad or separating two classes. But how do we choose the best classifier out of the lot? In this example we have three classifiers. They are all dividing the two classes or classifying the two classes blue and red. But how do we know which one is the best classifier? Maybe we can see the margin of the classifier. Based on that we can find out the best classifier from a given lot. So look at these two classifiers. This is classifier 2, this is classifier 1. So if you see the margin, what is margin? From the classifier to the nearest data points, what is the margin, what is the distance? Looks like classifier 1 has large margin, classifier 2 has slightly lower margin. Now the one that has maximum margin, the classifier that has maximum margin, does a good job of generalizing, or it's a good model compared to the one which has a smaller margin. But why? How can we prove that the classifier with large margin is good at generalizing, works well on the new data points? Let us take an example of these new data points. These are the two new data points. They are pretty much at the same location in these two graphs. Classifier 1 still holds good. It is still doing a good job of separating them or classifying them accurately. Red dot is classified as red, blue dot is classified as blue. Whereas classifier 2 failed in both the cases. Here this triangle, blue triangle, is classified as red and red dot is classified as blue because it has a smaller margin on the new data. It is working well on the training data set, but when we take a testing data on new data points, classifier 1 with the maximum margin works better compared to classifier 2 with a smaller margin. So what is the best decision boundary? A decision boundary or a classifier with maximum margin is the best classifier. So look at two models or two classifiers, M1 and M2. M1 has larger margin. M1 is closer to the data points A, B and C. M2 is also a classifier which is classifying these two classes, but its boundary is decided based on C, D and A, or A, C, D. So the best classifier out of these two will be M1 because it has large margin, and we have already seen an example that classifier with large margin does good generalization. That is the reason why for a given data set, a classifier that has maximum margin will have maximum training and testing accuracy. So we would generally prefer to have a classifier that has maximum margin. Let us see an example of how to build a simple classifier. Simple classifier is nothing but something like logistic regression model, where we just get a decision boundary to separate class 1 from class 2. So in this example we will try fraud transaction data, and we will try to fit a logistic regression classifier and draw a classifier plot on that data. So here is the data set, and this is just a simple transaction data where transaction amount is there, transaction count per week is there, and whether it is fraud or not fraud ID is there. So we will just fit a logistic regression model that will identify fraudulent transaction depending on transaction amount and transaction count, and then we'll try to draw a decision boundary on the space of the data or objective space. So these are fraud transactions, these are non-fraud, whatever is the definition, and these two classes have been divided by logistic regression using this line.